Hello everyone. In this worked example, we're going to use the method of composite parts to identify the magnitude and location of the equivalent point load for the distributed force shown below. And then we're going to use that to identify the reaction forces at supports A and B, which are each 1 foot from the edge of the beam. So we've got 1 foot this way, 1 foot this way. Alright, so starting this problem, step number 1 is to identify the equivalent point load, and to do that we're going to use the method of composite parts. And we need to break things down into pieces. So we've got, if we look for basic shapes, we've got a rectangle here, another rectangle here in the middle, so rectangle 1, rectangle 2, and then shape number 3, the last 6 feet, is a triangle. So those are my 3 shapes, and I'm going to use those to find the magnitude and location of the equivalent point load. So moving down a little bit, I'm going to have my 3 shapes, so put together my table. So I've got shape over here, so shape 1, 2, and 3. Alright, and with this I need to know the area, and the units on that are going to be pounds actually. So if I've got a width of feet, a height of each of these of pounds per foot times feet is going to give you pounds. And then in terms of the other piece, we need to know the centroid or x-bar of each of these 3 pieces. So the centroid of the rectangle, somewhere around here, centroid of this rectangle, somewhere around here, and the centroid of the triangle for shape number 3. Each of those is going to be in feet. And we're measuring everything from the left over here. So this is my origin point right here. Alright, so shape number 1, it's just a rectangle, so base times height. So 40 times 2, I have 80 pounds is my area. Shape number 2, it is another rectangle, so 60 times 2, base times height, is going to give me an area of 120 pounds. And then number 3, I've got a triangle, so it's 1/2 base times height. So the height is 60, the width is 6 feet, so 1/2 times 60 times 6 is going to give me 180 pounds is the area of that last piece. Alright, in terms of centroids, alright, so this first rectangle, the center point of that first rectangle is just going to be 1 foot. So it is 1/2 of the overall base. The centroid of the center rectangle is going to be out 3 feet. So I go 2 feet just to get to the rectangle in the first place, another 1 foot to get to the center of this rectangle. So this one here is going to be 3 feet. And then finally, to get to the center of the triangle, I have to go 4 feet out just to get to the edge of the triangle. So here's the right angle in my right triangle, and I have to go 1/3 of the way out in my triangle. I can look that up in my centroid table. So 1/3 of 6 is another 2 feet. So 2 feet plus 2 feet plus another 2 feet. It is 6 feet to get out to the center there. Alright, now I've got my table filled in. I can do my calculations. So FEQ, the magnitude of my equivalent point load, is going to be simply the sum of the areas. So 80 plus 120 plus 180. Alright, so 80 plus 120 plus 180 is going to be 380 pounds. So that is one thing I'm looking for. For the location, XEQ, I'm going to do area 1 times centroid 1, so 80 times 1 plus 120 times 3 plus 80 times 6. Divide that by the overall area. So here I'm going to have 80 times 1 plus 120 times 3 plus 180 times 6. And all of that gets divided by the overall area, which we already calculated, that's just 380. All right, so if I run those numbers through a calculator, I get an XEQ of 4 feet. So actually a pretty even number. All right, so I'm going to use FEQ and XEQ and redraw my beam with just a single point force. So for that, I'm going to jump to another page. All right, so what this means is that if I had a beam and I've got my two supports here at A and here at B, my equivalent point load would be a magnitude of 380 pounds, and it is a distance of 4 feet from the left end of the beam. All right, so if I get rid of my supports and just draw in the normal forces, I'm looking for FA and FB. FA and FB. I'm going to look back and see the dimensions. So A, I know was 1 foot from the end, that's stated in the problem, so it's 1 foot to get to A, and then to get to B, so it's a total of 10 feet long, so B is 9 feet out. So this is 1 foot, this is 9 feet. All right, so that should be enough to solve for FA and FB. So I look at my equilibrium equations. I have my free body diagram now. So sum of force in the x direction is 0 equals 0. It's not all that helpful. There's just nothing in the x direction. In the y direction, I'm going to have FA plus FB minus 380 is equal to 0. That's my equilibrium equation for the y direction. And then if I take the sum of moments about, let's do about point A. So the sum of moments about point A, which is where FA is applied, what I'm going to have there is FB times 8. So force times distance. And it's a counterclockwise, so that's a positive moment. Minus 380 is my force times my distance. So A to this force is 3 feet. That must be equal to 0. And this is negative because it would cause a clockwise rotation, which is negative rotation. So if I take this moment equation, basically FB is going to be equal to 380 times 3, divide that whole thing by 8, or FB is going to be equal to $142.5 pounds. So that's one of the two numbers I'm looking for. To find FA, I would simply take, so FA plus 142.5 minus 380 equals 0. So 380 minus 142.5, kind of rearranging this sum of forces in the y equation, I get a FA value of 237.5 pounds. All right, so over on the left over here, FA is 237.5 pounds. Over on the right at FB, that is 142.5 pounds. All right, so that's all we've got for today's worked example. Thank you for watching. Hope to see you again.